Hello everyone. I'm going to be talking about Thevenin equivalents in AC circuits. Now, before you study this section of the course, you have to make sure that you understand how to do Thevenin equivalents with DC circuits, okay? And then it'll be relatively easy to translate to AC circuits. If you're learning Thevenin with AC circuits for the first time, then learning Thevenin is going to be difficult. So, we can apply Thevenin to AC circuits, but for the Thevenin voltage, we are going to be using a phasor voltage for V Thevenin, okay? And for when we had R Thevenin, we're going to be using a complex impedance for the Thevenin impedance. So we're generalizing the circuits. So then, we have the basic concept of the Thevenin circuit here. We develop an equivalent circuit with a Thevenin voltage and a Thevenin resistance, and the same properties or characteristics of Thevenin for DC also apply. There is going to be such a thing as a open circuit voltage phasor and a short circuit current phasor. And then we have the basic relationships here that you'll recall from DC circuits for both now Thevenin and Norton equivalent circuits. And you should be quite familiar with the notation and concepts contained on this slide. All we've done is converted the voltages and currents into phasor form and generalized the resistance into an impedance. So this should be very familiar, and what's important to note is that the shortcut method to find the Thevenin impedance works the same way as when we had DC circuits with resistors, and the same restriction applies that we can only use the shortcut method when we have independent sources. And independent sources are the ones with the circles, okay? Voltage source or a current source, okay? Independent voltage source or an independent current source. So now let's get into our example and see how we can apply this. Okay, so now in this example we are to find the Thevenin equivalent at xy. Xy is here, okay? X and y is here. And we are assuming that omega is equal to 50 radians per second. It does not appear on any of the parameters in the circuit, so we're given it additionally to this, okay? And you know, these circuits can be given you in many forms. In this form, we've got a voltage phasor for this voltage source. We have a current phasor for this current source. So it could be given in many different forms, and you'll have to know how to translate them. So now, recall, when we're doing the Thevenin equivalent, we're transforming the circuit into its equivalent down here. So what stays constant are these points here, x and y. So there's 2 points, okay? That's how we can make a Thevenin equivalent. So then the circuit is equivalent at these 2 points. So no matter what you connect at these 2 points, whether you connect another circuit or make a measurement or whatnot, these two will be the same, okay? Functions the same at points x and y, okay? That's a basic concept. So then, if we were to measure the voltage at x and y, we should get the same voltage on both. If we put a wire across both of them, we should measure the same current flowing through that wire, okay? For them to be equivalent. Okay, so then, let's continue how to solve this, okay? So our first step is going to be to convert the impedances. We're working with AC, so we're going to have to convert, you know, our inductor and our capacitor to their impedances, to their complex impedances. Okay, and So then, just as a little quick reminder, the impedance for the resistor, we have two resistors, they're both 10 ohms. That's already in a impedance form, and it's 10 ohms, just the way it is. So that's fine. So let's do the next one. Let us do the impedance for the inductor. So the inductor is here, and its value is 0.1 henries. And we know the equation is ZL, the impedance for the inductor is J omega L. So we know what J is. 50, that's omega, and that's coming from here. That's the radiant frequency, and 0.1 is, of course, 0.1 henries. And that works out to J 5 ohms. And then ZC follows the same format. We know the equation is 1 over J omega C, okay? And then we know that omega, it's the same, omega 50, and then C is 2,000 microfarads, and that's what's down here, 2,000 microfarads. And that works out to minus 10 J ohms for the impedance of the capacitor. So then we'll just put in the values here in our drawing just to keep a record of them. So then, like our next step here, we're going to convert the voltage and the current phasors to rectangular form. And the reason why I'm going to do this is because I know a little bit later I'm going to write an equation, a node voltage equation, and I'm going to be adding up these numbers. So rectangular form is the most convenient form to add the numbers. Okay, so we're going to convert the phasors from polar form to rectangular form. Okay, so let's start with the voltage phasor. So we're doing the voltage phasor, and we'll just plot it here, okay, just to visualize it. Our magnitude was 100 and a phase angle of 45 degrees. So that's what we've drawn in our little drawing here. Magnitude 100 with a phase angle of 45 degrees. And what we're doing is finding what the value is here on the real axis and what the value is here on the imaginary axis. So then we say that the voltage phasor is equal to 100 cos 45 degrees plus J100 sine 45 degrees. Just simple trig. And that works out to 70.7 plus J 70.7. So that's a rectangular form for the voltage phasor. And now let's do the current phasor. And the current phasor is here, and it's 5 at a phase angle of 0 degrees. So that's, if we were to just draw that, you know, if we have the real axis and the imaginary, that's just 5 over here, right on the real axis. It's just 5. Okay? So that's what we've got here. So that's simple. So then we can populate those values in our drawing to keep track of them. Okay? And then what's our next step going to be? We're going to perform node voltage analysis at X with the ground reference at Y. So we're going to do node voltage analysis. So let's label it properly. So we're going to do node voltage. So we're going to denote this voltage as Vx, or in phasor form, right? And then we're putting the ground reference over here. And we'll note that when we solve for that, that is going to be the open circuit voltage, right? So it's going to be the open circuit voltage, VOC, however we want to write it. And we know that that's equal to V Thevenin. Okay, let's put the phasors on there. Okay, and so note here, when we find Vx, we're going to be at the same time finding V Thevenin. So let's calculate our node voltage. Okay, so now in constructing the node voltage equation, it's exactly the same as what we've done in AC. We consider the node that we're on to be the highest voltage and that all currents are flowing out from it. So we have this current flowing over to the left, and we have that in our equation. We start with Vx. The other side of the resistor is V, so that's pretty straightforward. So it's minus V. and then the impedance in the middle is a 10 ohm resistor, and that's what we see here. So that was pretty straightforward. So then we go down, okay, the first one going down through the inductor and the capacitor. So that's this one in the equation here. So the voltage we're starting off, it's Vx, and we're going to the ground reference, so the other side is 0, so we're not going to write minus 0, so it's just Vx on the top. And then we write the impedance in that branch. And so then we have two components in series. We have the inductor and we have the capacitor. So that's what we're writing down here, ZL plus ZC. Hope that makes sense. And then we'll do the next one, the current down in this branch, and it's opposing the current of the current source, and the value for that, or the label for that, is I. Okay, so we have a minus I there. So everything should be fairly clear from a point of view of a DC circuit analysis. And then we have the last current going through the 10 ohm resistor, and that is just the last term here. We have Vx minus 0, and then going through the 10 ohm resistor, and everything equals 0. Now note that, you know, I didn't write the current going this way, right? What's I equal to here? Well, it's an open circuit, so I is going to be 0, so I don't have to write that. That's why that doesn't appear. Okay, so then let's work our node voltage equation that we've developed. So we're going to sub in the values that we've got. So we've got, you know, we've got a value for V there, and then we'll put in the values for ZL and ZC, put in the value for I, and we already had the values for the two 10 ohm resistors, so that's that. And our variable is Vx, okay? So then, if we multiply by 10 to simplify, we get the expression here, Vx minus 70.7 minus J70.7, and then plus 2JVx. And there's a missing step here, so I'm just denoting it. I just simplified the denominator there. J5 minus J10 results in minus J5, okay? And then we continue. We have minus 50 and plus Vx. And then we can solve for Vx, just some straightforward manipulation, and we get a value of 47.85 minus J12.5. Now, we're not finished yet. This is a rectangular form for the voltage, and notice that over here we want to have the Thevenin voltage in the time domain form. So now what we have to do is we have to take the rectangular form of the voltage phasor, which this is V Thevenin, as you recall, right? Remember, that's V Thevenin. So we have to convert that into polar form. Okay, we have to convert this into polar form, and then the time domain equation will fall out very easily from the polar form. So we can't go directly from the rectangular form into a time domain. We have to go first into the polar form. Okay, so let's do the calculation. So let's draw this out. So then we have 47.85. That's the real number, so that's that point. And then we have minus J12.5, and then this is that point, okay? And then what we're going to do is we're going to calculate M. That's probably not going to show up very nicely, but we're going to calculate M, and we're going to calculate theta from that, okay? So that's just a little bit of trigonometry that we're going to do. So M, we're just going to use Pythagoras. So it's just the square root of 47.85 squared plus 12.5 squared. Okay, so that's the magnitude. So that's the length of that vector. And then the phase angle theta is going to be the arctan or inverse tan of minus 12.5 divided by 47.85. Okay, so then that works out to 49.5 0.5 and a phase angle of minus 14.6 degrees. And that's our V Thevenin. Okay? And then it's very straightforward to come into the time domain. So let's just make sure we see what's happening here. The 49 drops down, and that's what multiplies the cos. And then the phase angle drops down here, and it subtracts. Okay? And then where does this 50 come from? This 50t. Okay? T is always going to be coming back, but the 50 is coming from here. Okay? It's 50, it's omega, it's the radiant frequency, and it was given to us, so that is coming down here. Okay? So we found the time domain expression for the Thevenin voltage, and let's put that into our drawing. So that's our first result, okay? And now what we're going to do is find the Thevenin impedance. So now there's two ways of finding the Thevenin impedance. One way is if we connect the wire here and calculate I short circuit, and then from that calculate the Thevenin impedance. But in this case, we notice that we have only independent sources, an independent voltage source and an independent current source. So we can use the shortcut method. And when we're doing that, we have to zero the sources. So what does that look like? We're drawing the circuit here, and we've zeroed the sources. So we've zeroed the voltage source. So when we have a voltage source, when we zero it, that means that its value is 0 volts. So there's 0 volts across it, and that becomes a short circuit, or it becomes a wire. Okay, so that's what this is showing. And so we have a wire, and we've just put the little red dots around it just to show that there was something there, okay? Just to be explicit in our work. And then for the current source, we take that out because we zero the current source, so it becomes 0 amps. So there's no current flowing through that current source. And whenever you have any circuit element that has 0 current flowing through it, you can remove that circuit element from the circuit, and it won't change anything with regards to the circuit. Okay, so we can remove that current source, and we've denoted that the current source was there with the dashed red lines. And then all the other components stay the same. All the passives stay the same. The resistors, the inductors, and capacitors all stay there. So then let's see how we're going to calculate this. We can see that there's some parallel branches, okay? This branch is in parallel with this branch, is in parallel with this branch. So try to visualize that if you're having problems, and the equation that I've written down here expresses this. So the 10 ohms is in parallel with the series combination of the inductor and the capacitor. Okay? That's what that's saying. So it's a series combination of the inductor and capacitor in parallel with the 10 ohms, and then that last 10 ohms is in parallel with the other two branches, okay? So then let's simplify this. So then I notice that the 10 ohms is in parallel with the 10 ohms, and I know whenever we have resistors or impedances that are the same value in parallel, we just divide by the number of those elements that are the same value in parallel. So we have 2 resistors, so we just divide by 2. So it's a little bit of a shortcut. We can calculate that out. If you don't believe it, use the formula to calculate parallel resistors and check that you get 5 ohms for this. Okay, and then what I've done here is I've just added these together. J5 minus J10 is J minus 5. Okay, so then these two elements are in parallel, so let's use the parallel formula. In the parallel formula, one of them is that you multiply the two impedances together on the top, so that's the top, and then you add them on the bottom. So that's what we're seeing there. Okay? That's the parallel rule that should be familiar to you from resistors, and it applies for impedances as well. So now I've just factored out 5 from the numerator and the denominator, right? So I've just gotten rid of a 5, and a 5, okay? So that's what I've got there. And then the problem is we have a complex number on the denominator. So there's not much we can do with that, so we got to convert it into standard form. And how we convert to standard form is by multiplying by the complex conjugate of the denominator, okay? So that's what we're doing here. And you notice whenever we multiply by the complex conjugate, all we're doing is flipping the sign from the number, okay? So this was a plus j on the right-hand side, on the left-hand side, and a minus j on the right-hand side, okay? And now, top and bottom have to be the same, okay? Because we are multiplying by 1. So we're not changing the original number, but we're getting rid of the imaginary number in the denominator. So you should be familiar with these operations, but this is just a quick refresher because a lot of people mess up this step. And then, so we multiply things out, so we get minus j5 plus 5 on the top, and on the bottom we get 1 plus 1. So we have to end up with a real number after we do that operation by multiplying by the complex conjugate. And if we don't get a real number, then we've done something wrong. This was the whole point. So now we can just simplify that to 2.5 minus j 2.5. So now, what does that mean? The Thevenin impedance is 2.5 ohms minus j 2.5 ohms. What on earth is that? Can I go to the store and buy such a component? Well, no, we're not finished yet. So let's see, how are we going to interpret this impedance of 5.5 ohms minus j 2.5 ohms? So how are we going to interpret this? Well, what is it that we know? We know that if we have a resistor, that's a real number. The impedance of a resistor is a real number. What about an inductor? If we have an inductor, the impedance is j omega L, which is basically an imaginary number times a real number. So now, if you understand where I'm going, why don't you pause for a moment and work out what this is, okay? But I'll keep going here. But if you already know what I'm going to do, then just try it out and see if you get the right answer. So then, for a capacitor, the impedance is 1 over j omega c. So if we bring the j upstairs, it's a negative imaginary number times a real number. So what if the impedance was a little bit more complex than this? What if we had a resistor and an inductor in series? Well, the equivalent impedance would be ZR plus ZL, wouldn't it? Okay, that's the equivalent impedance. So if we're drawing, the Z equivalent, it'd be ZR plus ZL, right? And that results anyways in a real number plus an imaginary number, right? A positive imaginary number. Okay, let's consider the next case. A resistor in series with a capacitor. So that's the ZR plus ZC. So then we have a real number for the resistor, and as we saw earlier, right from here, the capacitor's impedance is going to be a negative number times j, and then times a real number. So that is actually the form that we have up here, isn't it? Okay, so that's a real number minus an imaginary number. So the form that we have is this last one. Okay, so then we have our Thevenin impedance being a resistor in series with a capacitor. So now we know that the real part is 2.5, so that's the resistor part, okay? 2.5 ohms. Now, let's calculate for the capacitor. So we know that the impedance of the capacitor is minus J 2.5 ohms. And we know the impedance of a capacitor is 1 over J omega C. In our case, we know omega is 50, so we can put that in there. And we are going to solve for C. That's what we're solving for, C. So that's just a very straightforward manipulation. C is going to be equal to 1 over minus J 2.5 times J 50. And then that works out to 1 over 125 and works out to 8 millifarads. So we know the resistor and we know the capacitor. So then we can put them into our Thevenin equivalent circuit. So that part is our Thevenin impedance. That is our Thevenin impedance. So that is the final result. That is the Thevenin equivalent circuit of this circuit up here, right? So those two circuits will behave exactly the same if you're only considering points X and Y. You can make any kind of measurements at X and Y. You can measure the current, you can measure the voltage, or you can plug in a different circuit onto X and Y, and both of those circuits will behave exactly the same, and that's what Thevenin equivalent means. And from this you can easily get the Norton equivalent if you wished. You'll know that, of course, for the Norton equivalent, the ZT is going to be exactly the same, so that you'd only have to solve for the Norton current, which would actually be the short circuit current through here. But that's a problem for another day. Okay, so that was a Thevenin equivalent example.